Welcome back, geographers. It's more geography with Geography Geezer. What we're going to be doing in this video is looking at the beginnings of understanding the carbon cycle. Now, the carbon cycle is one of those modules that students tend to find the most difficult. I did a live on this last night, actually. People found this to be a useful introduction. But the problem was when you do a live, it's live, the lighting was rubbish. Sometimes I stumbled on my words. Giving you a more refined version of that overview that I gave last night so that you can benefit from crystal clear clarity and deeper understanding, not only of the elements that we covered last night in the live, but also how to apply this to different exam style questions. Let's go. So why students find the carbon cycle to be probably the most complex physical geography module, it takes a real step up from the water cycle. If you consider the water cycle, we're looking at molecules of water. This can exist in a limited number of forms, essentially solid, liquid and gas. Carbon can exist in so many different forms. As a gas, carbon dioxide and methane. In living things, protein, fats, carbs, DNA. In rock, in this format, and in many other different ways. Now what you'll notice, and this is what I find quite useful in terms of what the carbon cycle actually is, carbon essentially hiding in all these different forms. It can move from place to place, and it will move via certain processes, and it will remain in certain stores. And that's what you've really got to focus on in those early stages of studying the carbon cycle. What we've got is what we term this grand biogeochemical carbon cycle, and this is broken down into your fast and your slow cycles. And the one you always start with is the slow cycle, so that's what we're going to go through in this video now. In doing so, what you'll also get exposure to is some of the major stores and some of the major processes that move carbon around the planet. The largest store by far is the lithosphere, and this contains 1 million gigatons of carbon. Now, the vast majority of carbon that's stored in the lithosphere is stored as sedimentary rock. And there is a significant quantity of the lithosphere that is also made up by fossil fuels. That represents around 4,000 gigatons. Now, the beauty with carbon is that it brings in so many other modules as well. It's a great synoptic module. You can always touch base with all the other physical geography modules and the human geography modules as well when you get into inquiry question 2. So what you can remember from tectonics is that the lithosphere is essentially what you would call crust. And we know that crust doesn't remain still. Crust moves. We've got these things here that are called convection currents. They move crust. We've also got slab pull down here that also causes the crust to move. And this is part of the first fundamental understandings of why the slow geological cycle is called the slow geological cycle, because as you know, crust moves in millimeters per year. That is very slow indeed. Now, a bit of recap as well. Let's say this is some oceanic crust. Let's say this here is some continental crust. Densities, as you know, are different, more dense, and therefore subduction will take place. Now, this is where I'm going to first introduce you to the concept of flux rates. So the movements of carbon between different stores. Subduction, or the kind of loss of lithospheric crust, if you like, destructive plate margins, takes place at a rate of around 0.6 gigatons of carbon per year. So it's always per year that it's presented. And usually it's in gigatons per year. Some centres will teach petagrams per year. I prefer gigatons. I don't know why, I just prefer gigatons. Now what we know happens here is there's enormous heat and pressure. This heat and pressure builds up, and what can happen then is this will become molten. Now remember, when something becomes molten, it's obviously warmer. When something becomes warmer, it becomes less dense. When something becomes less dense, it rises. And this is the magma rising. Followed in some locations, near plate boundaries, by a volcanic eruption. So we've got our first movements from what is a major store, the lithosphere, to another store here, which is the atmosphere. Now remember, what's really important in the carbon cycle is that you say carbon moves from to at this rate and in this form. So it's moving from the lithosphere, where it's currently in calcium carbonate form. CO2 is released here because of the increase in temperature. And remember, when things increase in temperature, they also release gases. And CO2 is being released via the process of volcanic outgassing. And this is occurring at a rate of 0.15 gigatons of carbon per year. So you've got all the fundamentals there. Formulating a good paragraph. Store from. We've got outputs from this area here. Subduction takes place at a rate of 0.6 gigatons per year. Calcium carbonate, sedimentary rock, oceanic crust, whatever you want to call it. Heat and pressure is applied, it turns it molten, becomes less dense, it rises, it releases gases along the way. Volcanic outgassing takes place at a rate of this, and then suddenly we have an increase in CO2 in the atmosphere. But one arm of the cycle, because where do we go next? That's always what you've got to think about with the carbon cycle. It's where next, because it's a cycle. It's going to go somewhere. Now you need to imagine the atmosphere is like the airport terminal. It's an airport terminal. There's so many different directions it could go. And if it's remaining in the slow geological cycle, it will usually take what I used to call a long haul flight. Now once in the atmosphere, where can it go next so it remains in the slow geological cycle? Well, what we do know is that CO2 can dissolve into water. That's what it does. It finds some water in the atmosphere and it dissolves into it. Chemistry students watching the video, it then becomes acidic. So we then create a weak carbonic acid, otherwise known as acid rain. pH, weak carbonic acid, around a 5.6. But what then? So carbon is on its way back down to Earth. It's left the lithosphere. Now what we need to think about is that it's a cycle, isn't it? So we need to get it back down to the lithosphere. So how on earth do we do that? Now what you might remember from coasts, if you studied coasts, is that chemical weathering can take place on limestone cliffs, calcium carbonate cliffs, however you want to phrase it, because of acid rain. Now the specific type of chemical weathering is known as carbonation, kind of obvious really. This process of carbonation takes place at a rate of 0.6 gigatons of carbon per year, roughly. You will see certain sources that might say it's 0.8. To be honest, it never remains as a constant, it really does vary, and we'll come on to that. So then this chemically weathered material is carried via this solution here. Now remember, dissolving takes place in situ. It is carried via solution. So remember, these things are now dissolved in the water. What we've got here is aqueous calcium carbonate. Aqueous calcium carbonate is essentially calcium carbonate being carried in water. Now carbonates have made their way into the ocean, so we're now in the ocean store. To recap the journey we've just been on: lithosphere, subduction, heat and pressure, less density, rises, releases CO2 into the atmosphere. CO2 combines with H2O. It's acid rain, then attacks a calcium carbonate cliff, chemical weathering takes place, and now our carbonates are in the ocean. Now these carbonates, they can precipitate, which means that they immediately kind of solidify, like when you put cream into something and it immediately sort of congeals into some solid stuff. But there we have solids. Now anything that's solid will eventually settle and fall to the ocean floor. So look, it is at the doorstep of the lithosphere, and we'll come back to this. The other way that carbonates can be used is if they are utilized by what we would call marine calcifiers. Crabs, mollusks, shellfish, whatever you want to call them, crustaceans, anything with a calcium carbonate exoskeleton can use these to form their shells. Now remember, it is the fate of all living things, sadly, to die. So these things will die. And again, these things will fall to the bottom of the ocean, to the ocean floor once more. It's very sad. But either way, this build-up over time, and we are talking a lot of time, will cause compression and compaction. This process here is known as sedimentation. And then, bada bing, bada boom, we are back into the lithosphere and we have our slow geological cycle. So how slow are we talking here? 100 to 200 million years. That's why it's called the slow geological cycle. Now to gain a more advanced understanding, and we really must, if you're aiming for A star to B, you've got to think of other concepts that we can bring into this cycle. Elevate the level of your response. Show the examiner that you've got a very sophisticated level of understanding of what's going on here. Now the thing that I teach my students is that this slow geological cycle is just one big negative feedback mechanism. Really important. Such an important concept in physical geography at A-level. Now, a negative feedback mechanism applies to any physical system that exists within a dynamic equilibrium. Negative feedback mechanisms. If we have a shift from the position of balance, either there's been increased input or increased outputs. A negative feedback mechanism is a series of processes that return the system back to the equilibrium position. And that's exactly what this does. Now the time taken, theoretically, and it is very theoretical, the time taken for this system to rebalance itself is around 100,000 years. So let's explore what we actually mean by this in terms of a negative feedback mechanism. We've got increased outputs from the lithosphere, so there is now a theoretical deficit in the lithosphere. Boom, we've lost some. We've also got an increase in the atmosphere. So what's happened is we've got increase in outputs and increase in inputs into this store here. We have an increase of CO2 dissolving into H2O. Therefore, we have an increase in the creation of acid rain. We then have an increase in the volume of chemical weathering that takes place. We therefore have an increase in the amount of carbonates that are created in aqueous form and are transported via solution to the ocean. And therefore, we have an increase in the amount of carbonates that make their way down to the lithosphere, and an increase in the amount of all of these particles that then undergo sedimentation. And thus we have balance restored once again. And then the system keeps going round like this, the equilibrium position constantly doing this. And that's why it's called a dynamic equilibrium, because it's constantly shifting. It's constantly shifting. Inputs. The Earth doesn't stay still, does it? The Earth does not stay still, and it's random chaos, complete random chaos. So that's the cycle. Now, we can't just stop there, because obviously we've got to think, what are some of the applications that we might have to consider of this content to different exam style questions? What I've been doing a lot of work on with my A-level students is this idea of perspective. So what we're often asked to do in 20 markers, sometimes in 6 markers and 8 markers, is consider the importance of things. That goes across paper 1, paper 2 and paper 3 in many respects. So importance is one of those things that can definitely be debated, and that's what we've always got to do with that A-level geography content. We've got to debate the importance. Now, there's a number of ways in which you can debate the importance of something. And when you are debating the importance of something, you're picking up those all-important AO2 marks. They are so important. These are the ones that are worth 75% of the marks that you will generate. 15 marks out of 20 is allocated to the AO2 stuff that you write down. Now, obviously, part of that AO2 is going to be AO1. If you don't know the content, then there's no way you can access all the AO2 marks. But this is all about how you think about things and how you debate things. So I give my students a list of 5 things that they can always consider the importance of anything within geography from. So we've got spatial scale, temporal scale, people, place, and futures and uncertainties. These will cover most of the stuff within your 20 markers, within your 8 markers, within your 6 markers, maybe even within your 4 markers. So let's just give an example. The importance of the slow geological cycle at spatial scales. We've got local and we've got global. I would say at the global scale, it's very important in regulating the composition of carbon in the atmosphere. The atmosphere is known as a global common. So you put anything in the atmosphere anywhere in the world, technically it could end up anywhere else in the world. Global commons. A fundamentally important concept within A-level geography, this idea of the global commons. There's only one other global commons that you could also consider, which is the oceans. And remember, the slow geological cycle also heavily involves the oceans. So therefore, we've got its importance at the global scale. Now, I would say that it's probably most important when you consider it at this scale. Those words there, like most, more, least, less, these are the debate words. This is the language that you need to be using. This is the language that you need to be associating with every single aspect of the study of A-level geography. So when you're going through content with your teacher, or when you're revising for content, when you're revising for any mocks coming up, revise it from these perspectives. In future videos, I'll show you how you can use these perspectives to structure your 20-mark paragraphs. And this is something that we do in my online group tuition courses. Point to pause there, to be honest. Just released an outstanding offer, if I'm honest. For the rest of November, you can gain access, you can lock in your revision process. The revision process next year takes place from March to June, and it is a program that will take you through exam technique for papers 1, 2, and 3. Not only are we covering exam technique, we're also covering the content. One of the most popular things that I did last year was an all-day core content session right before the exam. It was a day dedicated to just touching base with all the absolute core elements of every single module across the board. Tectonics, coasts, water, carbon. I did the same for paper 2 with globalization, superpowers, regen, diverse places, migration, health, human rights and intervention. And then those that were part of the full program were taught how to use it. If you're interested in joining, the link is in my bio. Now this is running for November, potentially December. You can access this for £9.99 a month. £9.99 a month over the next 10 months. Don't miss out on this. Program last year, just to put it into perspective, was £499, so you need to lock this in now, seriously. Those students who were on that part of the course, the vast majority of them were gaining A's and A stars. Anyway, back to this. I'm nearly done. So you can see, that's how you go through on the perspective. And then temporal scale kind of speaks for itself. It's the slow geological cycle, so it's the most important when we're considering the carbon cycle over the long term. The short term, probably more important to consider the fast biological, which, by the way, is going to be the content in my next live. I do my lives every Thursday, 6:30 till 7:30 without fail. Fast biological. We'll come on to that. So that's the end of the video. So there's going to be more content coming, there's going to be more exam technique chat coming, there's going to be more lives coming. Keep your eyes on the Geography Geezer channel, okay? And if you haven't subscribed yet, I'd love it if you could give me a subscribe. Okay, thank you very much. See you again.